So the last topic of our lecture about deterministic inventory theory are the quantity discounts. We have already discussed the all units quantity discount, and now we will be looking at the incremental quantity discount. The incremental quantity discount now adjusts the prices for the unit quantities in specific areas, just giving the price to those units that surpass a certain amount. We see this here in the graphic. So we have a price C1 per unit given to those units who lie amount-wise in this range between Q1 and Q2. And for those units who are surpassing this amount per unit, we get a price discount, and so on, so that our total purchasing cost function looks like this. For that purpose now we want to determine how much we should order. So we need to adjust our total cost function with respect to this incremental quantity discount purchasing cost now. We can determine the purchasing cost as follows. We denoted C from Q because it's now dependent on our order quantity, which price we get, and we get the first price for those quantities who lie between Q2 minus Q1 in this area. The second price then for those who lie within the next area, this one, and so forth. So here we see that this is C1 J minus 1 for the last discount level that we get, plus the general or the last one where Q is now a range between QJ and QJ plus 1. So that would be the general form of writing it. To adjust our total cost function, we want to have the per unit purchasing cost. So we need to divide our purchasing cost by Q. And we redefine these intervals now with a new term. So we need a new denotation that is R from J. That is given by this range. And then we get the per unit purchasing cost as follows. Our inventory management regards, as you will recall, the total costs for ordering and holding in inventory. So we need also to determine the average inventory holding cost now. That is given by E multiplied C multiplied K divided by 2. That is the usual one that we know from previous derivations. And now we change the C to regard the incremental quantity discounts. So we set in the formula or the term or the expression for this purchasing cost per unit. And if we resolve that, we can see that here we can get rid of a Q, and then we get the following formula for it. The total costs now regard the purchase per unit purchasing cost that we have just derived multiplied by the demand. So this is the modification from the EOQ formula that we have seen beforehand. Then we have the fixed ordering cost or setup cost if we look at an internal ordering process, and our average inventory holding cost. So our total cost function looks now like the following. We have the following form that was the same for, or that is similar to what we have seen also for the EOQ formula, but now we have the speciality that depending on the quantities that we order, the prices get less because of the discount in the purchasing cost. So despite following the function throughout, we get a price discount for those items who lie between the different ranges. So our cost function has these two breakpoints. Yeah, we can have an algorithm that helps us to compute the optimal order quantity now. So in the first step, we would determine those ordering quantities for each of our levels that we denote as Q, J, star. And we obtain it by differentiating and setting to 0 the total cost function that we have just derived. This is the term where you should get for the optimal order quantity if you do the differentiation and the setting to 0. And here now we need to compute all the different order quantities for all the possible discount levels that we are facing. The next step is then that we check our derived optimal order quantities if they are within the feasibility range where we get actually the price for them. So we check for the range, and then we disregard those ones who are infeasible because the optimal order quantity would be out of this range. And then we would calculate for each and every of the order quantities that are feasible the total costs. And then, of course, we take the least costs, and this is then the optimal order quantity. This might sound quite straightforward, but it might be that you are unfamiliar with how to get to the total cost function and how to derive the optimal order quantity here. So this is what I want to show you now on the whiteboard. So first of all, just for sake of preciseness, I want to introduce some of the denotation that we here now we have the little q from j and they until m. And they are the order quantities defined at which our price will change. So at which the unit purchasing price changes. So they define the ranges where we get our discounts, and M is then the index that gives our discount levels. And then we have the C from J that gives the unit purchasing cost factor. And we assume that we have C1 that is larger than C2, larger than etc. until we reach the last discount level. Okay, our goal is now to determine the optimal order quantity that gives the total minimal costs. And we have seen in the lecture slides the purchasing costs that are given by C from Q, so the prices that depend on the order quantity, and that was C1 multiplied by within the range for the first price plus the range for the second one, etc. And just to formalize it, the quantity level before the level J is defined as follows, and then we have the price for the last discount level where we have the discount, the quantities given as follows, where we have now the Q that is between Qj and Qj plus 1. These now we give a new denotation that is R from J. So if we write this in the short form using the R, then we can rewrite our purchasing costs as R from J plus Cj multiplied by Q minus little q from J. So that is useful for deriving the total cost function. You will see further on. We need now or we want to have the per unit purchasing cost. So we need to divide our pricing scheme by the quantity that we will order. So we need to do that, of course, then also for all the terms. And if we do so, then yeah, you will see further on. Now we need the average inventory holding. So that was the purchasing cost that depend on the order quantity. And now we want to see or derive the average inventory holding. That was given by the formula E, the interest rate, multiplied by the price, multiplied by the order quantity, and this divided by 2. This was what when we derived the EOQ formula, we called also our inventory holding cost factor H. Now we regard it for the pricing scheme and the interest rate. And we can use now here or set in the per unit purchasing cost for our Q. So this becomes then E multiplied by CQ divided Q. And here we had also a Q standing. And this is the average, and we can use the Q here. And then we have the following easy formula for the average inventory holding. Now we put these terms together to formulate the total cost function that we called zeta of Q. And this is now given by the per unit purchasing cost multiplied by the demand. So C from Q multiplied by the demand rate divided by Q. You can check also how this was in the previous formulas. Then we have the fixed ordering cost or setup cost. And the inventory holding costs. we sit now in the terms that we have derived beforehand. So this was for the per unit purchasing cost, we set in Rj divided Q plus Cj minus Cj multiplied by Qj and Q. This was, I highlighted so that you know where these terms come from. So these are the per unit purchasing costs that I set in here at that stage. And we should not forget that this is to be multiplied by D. Then for the fixed ordering cost, they stay the same. And now we modify our inventory holding cost accordingly. So to highlight where I got this term from, this part here is given here. That were the purchasing costs. So I set, we refined it here in the formula. So I just set in this term. You may realize that this formula doesn't look too easy, and what we will be doing to find the optimal reorder point is that we differentiate the total cost function, and then we set it to 0, so we differentiate for Q, and then we would set it to 0. So we are interested, or we differentiate for Q. So we have, and Q finds itself here, I highlight it in blue. So it's with this formulation, it's quite difficult to differentiate, so we can make the job easier in rearranging the terms that I want to show you now in the extensive version, so that you can actually see what I'm doing. For those who are familiar with that, of course, can skip this part. So first thing that I would do, I want to resolve or get rid of the brackets, and therefore I multiply each and every term by D. I leave the key J, KD like it is, and here in the last term I could use to make things a little easier. So I'm trying to see how I can achieve this in putting, in losing the brackets and putting every term on its own fraction. And then I can see when I'm done that I have a Q here, Q here, here. That was it. In the denominator, so we have some of the fractions that have a Q in the denominator, and I can try to put them together and see if this becomes then more clear and easy. The rest stays as it is. Yeah, I don't want to write too much, so this is what I give here. Now we can see in the first fraction that we have a d here in every of the terms. So we can rearrange this and say d divided by q is then rj minus cj little qj plus k. That looks a little more friendly, and the rest stays as it is. Actually, I want to also now care for these three terms. So we have the ICJQ, where we have a q inside the term. So when we differentiate, then this term will remain. And the others, as you will see, will disappear. So here we can, I make it a little bit more elegant and put it again together in a bracket. So this is I from j minus qj divided by 2. And now you should have a easy time to see that the q is here and here. So this becomes more friendly when we want to differentiate now. So the differentiation goes as follows. We take zeta q and derive for q. Well, now we need to take care just of these two terms because they depend on the q. And the first term that we differentiate is minus d divided q power of 2. And then the bracket remains. And if we differentiate for the second term, then the I multiplied cj divided 2 remains. This term we set now to 0 because we are interested to get the optimal q. Also this I'm doing extensively, so you see every step that I'm doing for deriving the optimal q. Now you see I put this on the right hand side, and then we have minus and minus, so I want to lose the minus. Then we have dq power 2 multiplied by the bracket equals ICJ divided 2. Now we can take the inverse. And when we have done that, then this is in the numerator. I want to multiply then this goes in the denominator, so I'm multiplying with D, and everything that is in the bracket, I don't write it now because it's extensive writing. And this becomes then to be 2D multiplied by our bracket. I write it out now so you can see the terms. And this is divided by I multiplied Cj. And then what rests is losing the power of 2. And this we get if we take the square root. And when we do so, then I include the step now here, so I don't have to write too much. So our optimal Q is then the square root of this term. And this is what you find also in the lecture slide. So for calculating our example now, what we need to have is the formula for the optimal order quantity and the formula for our costs that is given here. So the data that we need for our exercise, parasol systems, were given as follows. We had D that equals 140, our fixed ordering cost K that was $30, and the annual interest rate that was 0.18. And in the first step, you can check this together with the lecture slides of the algorithm. The first step is to compute all the optimal order quantities. So we start with the first one, where J is 1. And I show it extensively, so you know what I'm doing. So we have R1 minus C1 for Q1 plus K. This is multiplied D divided ECJ. And at R1 we have defined that this is 0. So now we just need to plug in our data. So this is 0 minus first price 350 multiplied by 0 for the first quantity plus 30 multiplied by the demand 140 divided by annual interest rate multiplied by C1 350, and this is 11.54. So this is approximately 12 units. The next optimal order quantity is then 2 multiplied R2 minus C2 from Q2 plus K multiplied D is the annual interest rate multiplied by C2. This under the square root. And we have R2, which is now given in the following range. This is the price 350 multiplied by Q2 was 25 minus 0. That is for our first unit, of course. And this becomes 8,750 for R2 that we need here in our formula. So we need to calculate this price. And if we plug in our data, and the only one that was missing was the R2, and I showed you how to calculate it, so I'll leave that out. Then you should get 66.85, which is approximately 67. We have 3 quantity levels. So the third one is accordingly given R3 minus C3 multiplied Q3 plus fixed ordering costs multiplied by the demand. Now we need to take care how to get the R3. And R3 is given as follows. We have now C1 and the quantities for that price. Then the price for the quantities that lie within the next interval that we need to regard. These are all. So if I plug in our data, the C1 we have just calculated 8,750 plus this is now C2 was 315 and the range of the quantities was 50 minus 25 and this is 7,875. So in total we get for that price 16,625. This is our R3 that we need to plug in. And I think the rest, I make it extensively. So we have 16,625 for R3 and now 285 for C3 multiplied by Q3, that was 50 plus 30 multiplied by 140 for the demand, and this divided 0.18 or 18 multiplied by the price C3, and that gives us 114.8, which is approximately 115. Step 2 is now to check for feasibility of the optimal order quantities within the ranges. So Q1 was, I state the approximate numbers, but we do not have to round up. We allow for quantities that are discrete but infinitely divisible, so they can be fractional. So our first price range was in between 0 and 25, and with 12 this is feasible because it is within the range. The second optimal order quantity was 67. We are allowed this price range only in between 25 and 50, so this one is infeasible. So this one is fine, this one is not fine. And our third quantity was 115 approximately, and this was for all quantities higher than 50, so this one is feasible. Step 3 is for the feasible optimal order quantities to check their costs, or total costs. I show you one extensive example. So the first thing is we check the costs for Q1. And that is, I write the formula down, then plugging in the numbers is easier. Okay, so this is our formula. We need to plug in now our data for it. One last extensive version. Here I use the 12 units, so I'm rounding up. Okay, so if you calculate this together, you get a total cost of 49,728 for the costs for the first optimal order quantity, and now the ones for the third one. And let me just write you down the formula. So you know exactly what to plug in. You might wonder if you can use Excel for this work, and of course you can. My purpose here in deriving the formulas is to show you how this works, how the derivations and everything work, because that is the important part, to know what you are doing. plugging in numbers is then just a work. So here we have now these two costs for our two feasible optimal order quantities. And of course we take the one with the least costs, and this is for the 50 units. So our lowest total costs are given as follows when we order Q3 was 115. So optimal order quantity with incremental price discounts leads us to order 115 units.